This is the second of the two recordings for BIOS500 Lab 6. In this recording, we're going to talk about how we use SAS to determine confidence intervals for the population mean. And the formula we're going to ask SAS to implement is this one here. You can see that we're using the t-distribution based approach for calculating confidence intervals for the population mean. Now this formula is appropriate when you have either an underlying population which is known to be normal, or when you have a sample size that's large, and by large we've been discussing that we mean at least 40. At least when we're talking about the t-distributions, large is defined as at least 40. That comes from the Morn-McCabe's guidelines that have been discussed in class. Alright, so it's going to be quite easy actually to get SAS to produce this calculation for us. The difficult part is making sure this calculation is appropriate. In other words, the difficult part is making sure that you're comfortable with the assumptions for this calculation. Again, the assumptions are underlying population normally distributed, or sample meets Morn-McCabe's guidelines. If the sample size is less than 40, then actually what you're going to need to do is evaluate the other parts of Morn-McCabe's guidelines. They tell us that if the sample size is less than 15, you better take a close look at that sample and make sure that the sample data look like they're close to being normally distributed. If you have a sample size between 15 and 39, then the sample data don't have to look like they come from something that's close to a normal distribution, but at the very least you need to make sure there's no strong skewness or strong outliers. In other words, the sample data should be at most moderately non-normal if you've got sample sizes between 15 and 39 inclusive. So those are the things to think about, and we'll have to evaluate all that information before we go ahead and actually get SAS to do the confidence interval calculation. So I've got some more information in the notes about evaluating whether the normality assumption really is met or not, and we've been through ideas like this one in presentations in lecture 2, so hopefully this is not all new. Basically, if you don't know that the population's normal, and in real life you usually won't know that, and if you don't have a sample size that's greater than or equal to 40, then here's what you need to do. You need to figure out if conditions 1 or 2 from Morn-McCabe's guidelines are met. And you can do this using proc univariate. Basically, run proc univariate for the variable in question, the variable from which you're going to calculate a confidence interval, and look at the sample mean and the median to start off with. If those are reasonably similar, that's an indication that your data are fairly symmetric, and therefore they have that in common with a normal distribution symmetry. That's not enough, though. You've got to look at more tools, because assessing this normality assumption can be a tricky thing. So there are several more things to look at. One is the skewness statistic, which proc univariate prints out. We've briefly discussed this before. If the skewness statistic is less than 1 in absolute value, that suggests that your data come from a distribution that is no more than moderately asymmetric, no more than moderately skewed. And that's a good thing. So we're going to look for skewness statistics less than 1 in absolute value. Now this is a rule of thumb, I should point out, and not all statisticians agree on this particular rule of thumb, but we're going to go with it in our class, and it's usually worked out pretty well for me. The closer that skewness statistic is to 0, the more symmetric the data are, so the better you're feeling about your data having that property of symmetry in common with true normal distributions. Once you get skewness statistics more than 1 in absolute value, either smaller than -1 or greater than +1, now you're starting to get worried that the data really are too skewed to consider them to be no more than moderately non-normal. There's another statistic to look at too in proc univariate, the kurtosis statistic. If the absolute value of this statistic is less than 1, then your distribution has something reasonably in common, at least, with a normal distribution. The kurtosis statistic measures how much mass there is in the tails of your distribution. You know that for a normal distribution there's just a certain amount of mass in the tails. You remember the 68, 95, 99.7 rule. That's one way of thinking about how much mass goes in the tails of a distribution. Well, if your distribution has too much more or too much far less mass in the tails of the distribution than a true normal distribution, well, then you don't really want to think of your distribution as being normal, as being close to normal, right? All that I'm trying to say here is that if the kurtosis is less than 1 in absolute value, that means your distribution in the tails looks fairly similar to a normal distribution. At least it's no more than moderately non-normal, let's say. Once you get that kurtosis statistic more than 1 in absolute value, then you start to worry. Again, this is a rule of thumb. It's not universally accepted, and actually this rule of thumb is a little bit more problematic at times than the rule of thumb for the skewness statistic, but it should work out okay for most of our data sets, so we're going to go with it. Alright, so we're going to look at the sample mean and median, look at the skewness, look at the kurtosis. We'll also look at visual tools, the histogram. We're used to looking at those, aren't we? If we get a histogram which looks fairly bell-shaped, well, that reassures us that our data look like they come from a normal distribution. The more non-normal, the more non-bell-shaped the data, the more questions we have about whether normality is a fair assumption or not. I will point out that histograms can be difficult to look at when you have small sample sizes. It'll be a very sparsely populated plot with very few bars, maybe with lots of gaps, and it can be a little tricky to evaluate. That's life. One last visual tool, which is the normal probability plot. We've alluded to this in class. This is a plot of the percentiles of your data on the vertical axis versus the percentiles of a true normal distribution on the horizontal axis. The idea being that if your data match up well with a true normal distribution, then you should get a linear plot. Well, at least roughly linear. Nothing in real life is going to be perfect, so you won't get a perfect straight line, but at least a roughly linear plot makes you feel like yeah, things are looking roughly linear, roughly normal. The more exaggerated an S shape you see in the plot, or not just an S shape, but the more exaggerated any curvature is that you see in the plot, the more you start to worry that the data aren't that well matched up with a normal distribution, and so the normality assumption is not met. What you need to do with all these pieces of information, folks, is to look at them all and decide where the burden of the evidence lies. If just about all the pieces of information are pointing in the direction of grossly non-normal data, that is, more than moderately non-normal, well, then you probably don't want to use the t-distribution based methods for calculating confidence intervals that we're talking about on this page if you have a sample size less than 40, which is the only situation in which you need to worry about these other issues. Okay, on the other hand, if it's a much more mixed bag of information and several pieces of information are saying, well, you know, the data aren't any more than moderately non-normal, then you can probably go ahead and use the methods on this page, the t-distribution based confidence interval formula, because it turns out that method really is quite robust to mild or moderate violations of normality. I wish we could give you just one tool for normality assumption and say that's what you always look at, but it's just a trickier issue than that. You need to look at an array of information rather than one specific piece of information. You'll get used to it over time. Alright, well, this recording's getting long, so actually I'm going to split the recordings up into a third recording where we actually go through a data set and analysis and show you how to assess the normality assumption and how to calculate a 95% confidence interval for the true mean of that population. So although I initially said there would be 2 recordings, there's going to be a third one. Look for the third recording, folks.